ring of continuous functions on that space. So, right, so we have a topological space X, and then look at the ring of all continuous functions. For example, let's take real valued functions on X. And then the question is that can we reconstruct the space X given sufficient information on the structure of Cx, that is the ring of all continuous functions? And the answer is actually positive for compact Hausdorff spaces. So that is the main content of this presentation. So first, let's recall the subspace topology on the maximal spectrum of Cx. So we define this Zariski topology on the whole spectrum, that is the set of all prime ideals of this Cx. So you restrict that topology to the subspace maximal spectrum of Cx. And quickly we can see that this subspace topology has a nice basis. We know that if you consider an element of your ring of continuous function, take some f, which is a continuous function, and look at all the prime ideals which do not contain f. So we denote that by xf. And we know that that forms a basis for the Zariski topology on the spectrum. So if we intersect those xf with the maximal spectrum, then obviously we get a basis for the subspace topology for the maximal spectrum. So basically now we have to look at all maximal ideals such that a particular element is not contained in the maximal ideal. So this collection will form a basis for my subspace topology on the maximal spectrum. So yeah, so we know the basis for the subspace topology. And next, we try to characterize the maximal ideals of this Cx. And now the property of the space will come in handy. So, so let's see. So let's look at the ring homomorphism, which is basically an evaluation at the point X. So basically, you take a point, you take a function f in the ring of continuous function, and you fix a point small x in that space, and you send f to fx. So that is our evaluation map from Cx to R. And obviously this map is a surjective ring homomorphism because constant functions are there always. So you can take any constant function and that will give you every real number in the image. So that is a surjective ring homomorphism. So then look at the kernel of this. So what is the kernel of this? All possible f's such that this evaluation gives us 0. That is my kernel of that evaluation map. And then by first isomorphism theorem, the Cx quotient, the kernel of this map, will be isomorphic to the image, which is just real number because it's a surjective map. And you know that R is a field. So obviously this kernel will turn out to be a maximal ideal. So we know that if we look at all possible f such that those f's vanish at a particular point x, so that will give me a maximal ideal. Now this is the easy part. Now the converse is interesting. Actually, we will show that any maximal ideal of the Cx is of this form. So we denote this kind of maximal ideal by mx. So mx means set of all functions which vanish at a fixed point. And we will show that all maximal ideals will be of this form. And that will precisely use the topological property of the space X. So let's take a maximal ideal M. We are taking a maximal ideal M, and let's say it is not of the form mx. So that means, okay, let me draw a picture. So this is my space X, and this is real number. Suppose this is my space X. So if my maximal ideal is not of the form mx, that means for all x belongs to x, I can find a function such that f does not vanish at this point, isn't it? Because I'm assuming that the maximal ideal is not of the form mx. So for every x, I will get a f which does not vanish at that point. So now use the continuity of this function. So what will happen is that my x will have a neighborhood, let's call it vx, such that my fx, I mean my notation, in my notation, just f sub x does not vanish on the open neighborhood vx. And then what we can do is that we can cover the whole space capital X by the small neighborhoods. So that will give me a open cover for this space X. So now use the fact that my my space X is compact. So that will give me a finite collection of open sets vx1, vx2 up to vxn, which will cover the whole space X. So I mean for each vxi, basically you are having a function some fxi, so that it does not vanish on this neighborhood. And then what you do, it's a standard trick. You define a new function which is the sum of the squares of those fxi's, and clearly this new f will belong to my maximal ideal. But the thing is that this f does not vanish at any point of x, isn't it? Because if f has to vanish at some point of x, some fxi has to be, I mean, 0. And we know that we can find a neighborhood such that that particular fxi does not vanish there. So that means f does not vanish at any point of the space x, but this f belongs to the maximal ideal. So that means this f is a unit, so which is not possible. Yeah. So right. So that's what I was saying is that f does not vanish at any point of x. So my f is a unit, but any no unit can belong to the maximal ideal. So that's a contradiction. So we have shown that every maximal ideal has to be of that form. I mean, you take a particular x and look at the collection of all functions which vanish at that point. That will give you a maximal ideal, and these are all. So we have completely classified all the maximal ideals. Okay, so up to now, everything is okay for everyone.
Yeah.
Okay.
Yeah, I think it's fine. Yeah, good.
Yeah.
Next step.
So now a small observation, which is that if my x is not equal to y, if my x is not equal to y, then my mx and my are also not equal. Okay, just wait a second. Something is happening. Yeah. So if x and y are two different points, if my x and y are two different points, then the corresponding maximal ideal will also be different. So for that we use some topological property of the space X, which is that if my X is Hausdorff, then you know that my points are closed. Right. So in a Hausdorff space, obviously the points are closed. And there is a standard fact in topology that any compact Hausdorff space is normal. So basically, by means of Urysohn lemma, what normality means is that we can always separate two closed sets by a continuous map. So what does that mean? So if A and B are two disjoint closed sets, so then you can define a continuous function on the whole space X such that the whole of A goes to 0 and the whole of B goes to 1. So this is what we mean by separation of two closed sets. And by Poisson lemma, this is always possible if my X is compact Hausdorff. So then, given any two points X not equal to Y, I can find an F such that this X goes to 0 and this Y goes to 1 by the separation of two closed sets, which are basically singletons here, X and Y. So my F belongs to the maximal ideal Mx, but it does not belong to My. And that clearly shows that Mx is not equal to My. So what we have done is that we have classified all maximal ideals. Any maximal ideal is of the form Mx. And then we have showed that if X and Y are two different points, the corresponding maximal ideals are also different. Yeah. Now, on the other hand, we will calculate a basis for the topology on the space X. And this is an interesting basis because this basis is defined in terms of the elements of the Cx, which are basically some continuous functions. So basically, you look at this open set, UF, which is just the set of all X is that if does not vanish at that point. So these are the kind of open sets we want to look at. So that is what I have written here. UF is an open set since F is continuous. So now what happens is that, so you take a point X in the space X, and then you look at some open neighborhood of this. So then you know that this U complement is a closed set. And this singleton X is also a closed set. So again, use Poisson lemma. So then what happens is that we can find a function F such that the F takes takes the value 1 at the point X and it takes 0 outside U. That is again by Poisson's lemma. So what is happening is that this point X actually belong to my UF by definition. And by definition, UF is the set of all X such that F does not vanish there. So obviously UF is contained within U because outside U F vanishes. We have produced F like that using Poisson's lemma. So for every point X and every neighborhood, open neighborhood U, you can push another neighborhood UF, which lies within that. So that again shows that this collection UF actually forms a basis for the topology on X. So yeah, so that is my basis. Okay, then so remember that our goal is to reconstruct the space X given the information on the maximal spectrum of this. So somehow we will try to show that we will try to define a homeomorphism from X to the space maximal spectrum of Cx. And we can easily guess what the map can be. There is a natural map, which is that just send a point X to the corresponding maximal ideal Mx. That is my map. And we have already shown that this map is surjective because we have proved that every maximal ideal is of this form. So this is also a surjective map. And also there is an injective map. That is also we have proved. So this is a bijection. And observe that we have calculated a basis for X, which is just my UF. This is my basis for the space X, and for the maximal spectrum of this, we have this basis UF tilde. We have defined this. And from the definition of UF and UF tilde, it's clear that, I mean, mu of UF is UF tilde. Just look at the definition. So I'll just go back to the definition. So my definition of UF is that set of all x is that if x is not equal to 0. And that means that my if does not belong to the maximal ideal mx. So that means by definition my mu of UF basically is UF tilde. And similarly mu inverse of UF tilde is UF. So mu is an open map and mu inverse is also an open map. So basically mu is a homeomorph.
So you define UF tilde this way or what?
Yeah, I defined UF tilde this way actually.
Okay.
Yeah. Yeah,
Oh,
there
I see.
could be
It's a
some difference in the
yeah, okay.
notation from the book, maybe. But yeah, I mean,
Yeah, right.
so this EF tilde is a basis on the right hand side, my maximal spectrum, and UF for the left hand side.
Okay.
Right, yeah. So just observe that we have explicitly used the topological property of X to characterize all possible maximal ideals of the all possible maximal ideal of Cx. And then by some elementary argument, we have shown that these are homeomorphic. So my space X is now homeomorphic to the maximal spectrum of Cx. On X, we have a compact Hausdorff topology. Compact Hausdorff topology. And on the right hand side, you have standard Zariski topology. So obviously, if you know X, then you know Cx, and therefore you know maximal spectrum of Cx. But what we have shown is that the other way. Actually. If you know this space maximal spectrum of Cx, you can also recover your X up to homeomorphism. So topologically, they are basically equivalent. So that is all I had written, but I want to say something about. I want to say a little bit when the space is not, for example, compact. So yeah, so is it okay? So up to now.
Yeah.
Yeah.
Yeah, that's good. So go ahead.
Yeah, I will just say a few things, which is that, yeah, for example, take the space X, which is a 0 open interval. So which is not compact. This is not compact. This is not compact. And then you look at the ring Cx, which is basically my ring of all continuous function from 0, 1 to real number. And then obviously you know that if you define the map like X goes to Mx, so that will give you a maximal ideal, no doubt. For every X, you can construct a maximal ideal like that. Look at the all possible function which does not vanish. All possible function will vanish at that point. That will give you a maximal ideal. But the point is that every maximal ideal is not of this form. Is not of this form. So, for example, what you can do, you can take the ideal I, which is look at all possible continuous functions such that f of 1 by n is equal to 0 for all n, but finitely. So after some stage n, every 1 by n will give me 0. So clearly you can check this is an ideal, and obviously this is a proper ideal because 1 does not belong to this ideal. So this is a proper ideal. And then we know that this is contained in some maximal ideal. Some maximal ideal Cm. And then observe that this M is not of the form Mx for any x. So how can you see that? You can just draw some picture. So this is my 0, 1. So whatever x you can take, for example, take an arbitrary x, and then look at the function. So if you take an x, then you have some 1 by n here, and then some 1 by n minus 1 here, and so on. So you just define the function fx is equal to sine pi over x when x is less than or equal to 1 by n, and for x greater than 1 by n, you define something like x minus 1. So your function is just like this actually. Yeah, something like this. So below 1 by n, you take the sinusoidal part, and above 1 by n, you take the linear part. Then you can see that this function does not vanish at this point x. But this f belong to that ideal that we defined. So yeah, for every x you can do that. I mean, whatever x you can you take, you can find a large enough n such that 1 by n is less than x and apply this tree. So I mean, if my space is not compact, then obviously I do not have that kind of nice classification of maximal ideals. So obviously you have to take this compact space, compact Hausdorff space. Oh yeah, I think yeah. So I think that's all I had to say.
Okay, so you have another 10-15 minutes. So you want to add anything?
Okay, I mean, if it's okay for everyone, then I can do. Yeah. So I want to. Yeah, I can say a few things, which is that.
Yeah, please go ahead.
Yeah. On the Zoom, 10-minute time limit is left, so I will continue for 10 minutes. So, okay. So maybe I mean, few things I will say which you can take it as some exercise, or I will just give a sketch to prove how to prove these things. So yeah, so look at the space, the compact space 0, 1, and then look at the space C01, the ring of all continuous function from 0, 1 to R. Then you look at some point C, and then you look at the corresponding maximal ideal MC. So now you might think that, or one might guess that this ideal is exactly of the form x minus c. It's a principal ideal generated by x minus c. So the question is that is it true or not?
No, I mean, they need not be polynomials, right?
Yeah, but still, I mean, that's not the argument because not everything in this ideal is a polynomial. You can multiply x minus c by anything you want other than polynomial.
I think it's not true, but I don't know.
actually it's not. So maybe you can try to prove that. And then you can also, so this is some information on the particular nature of this maximal ideals, this MC thing. And then this is also a thing which is that M is not even principal. This ideal is not principal. It cannot be generated by a single element. Yeah, sorry, what is it?
Can you give an example why it is not?
Yeah, right,
Suppose
yeah, right. So also I think, yeah. So what actually you can show that MC is not even finitely generated. So these are more stronger results. MC is not even finitely generated. And the last thing is that MC is not even countably generated. So this is really a huge idea. MC is not even countably generated. So what you do is that, okay, you can try to prove it's not finitely generated. So let's say your MC is generated by some function, some f1, f2 up to fn. So then you can look at a new function f, which is just summation square root of my fi's. You can look at this function. So if all of the fi's belong to my maximal ideal MC, that is all of my fi's vanish at the point C, then f will also vanish at the point C. So f also belongs to my ideal MC. But then you can apply some analysis argument, just some standard delta epsilon argument to show that this f cannot be written as a linear combination of my fi's. Yeah, by linear I mean these CIs can be any function in the ring CX. Yeah. So CIs are some function in the ring CX, and this f cannot be written as combinations of this fi. So that way you can just show that it's not finely generated. And you can even show it's not countably generated. So what you have to do, you take a countable collection, just you take some countable collection in greater than equal to 1. And then you can look at the function instead of this instead of square root of fi. And then by some scaling, you can assume that every fi is less than or equal to 1, or say mod fi. So up to a scalar, I mean scaling, you can assume that every fi satisfies this relation, mod of fi less than or equal to 1, and then you look at the function summation square root of fi by 2 to the power n. I think this you can do.
okay. That's good.
Yeah. So why or I mean square root of fi, or here you just take, I think you can just take yeah, you'll just finish. You can just take mod here. So why I'm defining like this, because if my mod fi less than equal to 1, then this will have a uniform bound actually 1 by 2 to the power n. And then by Weierstrass M test, you know that this f will give me a continuous function also. So a priori it's not clear that if fi's are continuous, then mod of fi by 2 to the power n summation, that will give me a continuous function. But that follows from the Weierstrass theorem, Weierstrass M test. If all of your fi is bounded by 1. So this f is continuous, and also this f belongs to the maximal ideal MC. And then you can again apply some standard argument, standard epsilon argument near C, to show that this this cannot be written as some combination of this fi's. So this MC, these ideals are really huge ideal. It's uncountably generated. So Yeah, that's a nice information. So
Okay.
yeah, yeah. So yeah, that's all I think.
Yeah. Any further questions from anyone?
Or anything you want to add or something you can just tell.
There seems to be none. So who is the next speaker?
Aryan will speak next.